Mayday, mayday, mayday. Okay, so I think we'll get started with the second talk of the morning. I'll just pick up where Dragan left off, and a lot of what I do is just very simple calculation-oriented things, and it may be difficult or even more difficult than usual to take notes and keep up with all the calculations. So maybe it makes sense not to take notes, and then you can copy these beautiful pages and have them for your very own. So, but I know there's a percentage among you who are compulsive note takers who, no matter what I say, will write everything down. It's just the way it is.
So your notes are a little forgotten if you want to.
Yeah. So, okay. So let's pick up where Dragan left off last time. So you're interested in studying, say, in infinite dimensional unitary representations of G as SL2R. So Dragan gave a very beautiful argument why every irreducible unitary representation of a compact group is finite dimensional, but he was all the time averaging, which you can't do with using this non-compact group. So let's say in infinite dimensional irreducible, so there's going to be these guys floating around. So what are those? Those are our maps from those are continuous homomorphisms into bounded unitary operators on some Hilbert space, which sit inside bounded linear invertible operators on H. Okay, so one thing, if you want to study such things, one thing you could try to do is differentiate. This is a continuous representation, so you can try to differentiate, and so you get if you differentiate SL2R, you get the Lie algebra of traceless 2x2 matrices, and then this lands in some subspace of all complex endomorphisms of this Hilbert space. And this is a Lie algebra representation. So this means that d pi of the commutator of two traceless 2x2 matrices is the commutator of the corresponding operators. But the problem is that you're certainly going to keep track of some information about this representation by differentiating. You'll get something interesting. But you can't possibly hope to go backwards in any reasonable way with just this information of the differentiation. And the reason is very simple. The Lie algebra of the real line and the Lie algebra of the circle, well, you're just interested in the tangent space at the identity, and these have the same tangent space at the identity. So when you differentiate, you only keep track of this infinitesimal information around the identity, and you lose any hope of keeping track of what happens globally on the group. Okay, so differentiation is going to lose the topology of the group. Okay, so you want to keep track of more information about pi, and this global information that you lose from differentiating. So what does SL2R look like as a topological space? Someone said, what does SL2R look like as a manifold? What is it? Is it topologically equivalent to the real line? Is it topologically equivalent to, Pardon? Open donut. Okay, yeah. So from Castleman's lecture, we know. I think he said he learned it from a T. This probably goes back to hop fibration, I would think. But we know that SL2R, it certainly retracts onto a circle, right? I mean, it's the open donut. You can just squeeze it down to a circle. And it retracts, onto this K, which is cosine theta, sine theta, minus sine theta, cosine theta. So if we want to keep track of the topological information that we lose in differentiating, we can do that by, roughly speaking, just keeping track of the restriction of pi to k. So this extra information we want is pi restricted to k. Okay, so that'll keep track of what we're losing, roughly speaking, or a lot of what, well, you could hope to keep track of everything you're losing in this differentiation process. And as Dragan discussed, there's this isotypical, or this, should I call it the Ricci decomposition of pi into its isotypic spaces, which are indexed. Okay, so now I'm going to maybe use the notation, well, H was my Hilbert space, but for those of you who are going to copy my notes, I'm going to start writing V instead of H. And this is a direct sum. It's a Hilbert space direct sum. It has to be completed, but sitting inside here is the algebraic direct sum, which is dens here. So this algebraic direct sum, well, maybe I shouldn't circle that. I should circle this. This is the extra information we want to keep track of. This is what we want. Okay, so Dragan's going to define Harishchandra modules and GK modules a little bit more precisely. But let me just say what I'm going to talk about today, in this lecture now, is I want to classify all irreducible representations of this Lie algebra, GR, which is SL2R, okay, such that, well, the Lie algebra of K, KR, which is the Lie algebra of K, the algebra circle, that's pretty simple Lie algebra, it's just a one-dimensional one, acts semi-simply and with integer eigenvalues. Okay, so that's what this guy is. The Lie algebra acts by the differentiated action, and if I differentiate the action of K acts semi-simply with integer eigenvalues. Okay, so the hope is that, well, Harishchandra's insight is that this is an entirely appropriate question.
Are the elements of Vn automatically differentiable for G?
Yes, it'll turn out to be the case. So this is one of the things Dragan will prove, or probably not prove. But so indeed, this sketch. So there's no problem in defining this Lie algebra representation on this space. It's a good question. So Harishchandra's insight was that, well, at least for unitary representations, this keeps track of exactly enough. There's some notion of equivalence, algebraic. I mean, this is just a purely algebraic question. There's an algebraic notion of equivalence that corresponds exactly to equivalence of unitary representations. If I have one of these algebraic objects, it comes from a unique unitary representation, in some sense, and so I'll say that he discovered that this is an appropriate setting, a good setting for studying unitary representations of G. So you classify these, you classify, i.e., so i.e. this classification contains, as what we'll see is a proper subset, all unitary representations of G. So we start with the unitary representation. We get one of these. We get, if we just approach the problem and classify algebraically, we get more. We get things that don't come from unitary representations. But this is the setting, or this is the approach that Harishchandra took to classifying or studying unitary representations. Okay, so So the first thing I'm going to do is just complexify. If I have a Lie algebra representation of 2 by 2 real matrices without trace, I can just extend scalars and get a representation of the complex Lie algebra. And so let me do that. So let me rephrase this. So I want to rephrase. So refine or restate. So what I'm going to do, because the formulas turn out to be better, classify all irreducible SL2C representations such that, well, the Lie algebra of, okay, so what does SL2C look like? Well, it's C times, there's this upper triangular matrix, there's a lower triangular matrix, and there's a, okay, you guys are quick on the draw there. So I'll call this X, this Y, and this H. And you know the Lie algebra of K sits inside as +1, -1, but I prefer to work with diagonal matrix, so I'm going to conjugate K into this guy. So I'm going to classify all irreducible SL2 representations such that H acts semi-simply with integer eigenvalues. So I'm just switching so the formulas will become a little nicer. I prefer to work with this diagonal matrix. Okay, so let me just write down the commutation relations that you know. Hx is 2x, hy is 2y, and xy is h. Huh? Well, I sent an email. Everyone's supposed to learn finite dimensional representations of SL2C. So if you, huh? -2. Okay, see, they do know it, Bill. This is proof. They know it. So you know, you can just take the commutator of these matrices and verify these formulas. Okay, so now we can play a game. Okay. Well, I could do, this is not a very hard problem. You could, if you were trapped on a desert island and you had to get, huh? Oh. Okay, I put the comments in. This is not so, if you're trapped on a desert island, you had to solve it to get off, you could all do it. But the thing is that when you read accounts of this, you kind of read the polished epsilon over 10 argument. So I just thought, well, when I was preparing last night, I was thinking about how to do this. And so I do it as if I were trapped on a desert island. So I'm going to start with very familiar representations, the finite dimensional ones, at least if you did your homework and read my email, then you know the finite dimensional representations. And write them down in some sensible way. And then notice if I just relax some restriction on the finite dimensional relations, or this version of the finite dimensional representations, then I get a whole zoo of infinite dimensional representations. Now, the infinite dimensional representations will, in general, be reducible, but you can easily analyze the reducibility. I mean, these will be so-called principal series. You can look at the reducibility. They came up in Bill's talk. And what we'll find then is that the pieces of these principal series exhaust all of the irreducible representations. So that's what we're going to do. So we start with the finite dimensional one. And so let me just start up on the group because they're simpler to states, maybe simpler to write. So I'm going to write FD. Yeah, that's me. F of D is the span of over C of x to the d, x to the d minus 1, y to the d, and gx, SL2CX by change of coordinates. That is if I have a matrix A, B, C, D, and I act on x to the L, y to the d minus L. Well, I just take x to ax plus by, and I take y to cx plus dy, d minus L. So this is a irreducible representation. Well, we'll see it's irreducible. those are easy formulas to write. On the level of the group, we want to classify the Lie algebra representation, so I'm going to differentiate. Huh?
You define semi-simplicity?
Have I defined semi-simplicity? Oh, so what does it mean for H to act semi-simply? It's just so I'm talking about a representation of SL2C. So SL2C goes to an endomorphism of some space V, which I've started calling it V, okay? And what it means to be semi-simple is that pi of H is diagonalizable. So this is a pop-up window when you click on this word. Okay? So it says, I just want pi of H. There's some basis where pi of H acts diagonally. You don't like it?
No, in my mind, I have a definition. Is it the Killing form is non-degenerate or?
So that's that would what you're thinking of is what it means for a Lie algebra to be semi-simple. So there's the Cartan criterion that you're discussing is a way to test whether a Lie algebra doesn't have very many ideals. The only ideals are simple summands. This is the same word used in a different way, and this is what it means in this context.
Oh, I see.
So
I confuse with, I seldom see the same means diagonalized.
okay, so maybe this is just I don't know where I picked up this terminology. Maybe it's non-standard. So anyway, so if you don't, how about acts diagonally? Diagonalizably with integer eigenvalues. Okay, good. Okay, so let's take this and see what we get on a. So let's see how H acts. So as I said, these are calculations that you've all done before, but let's just warm up a little bit. So how does this element H act on this basis vector of this representation? What am I supposed to do? The way the Lie algebra representation is defined, I'm supposed to look at how e to the t 0 e to the minus t acts on x to the L, y to the d minus L. And well, when I change coordinates, I'm going to get an e to the t raised to the lth power and e to the minus t raised to the d minus lth power. So I'm going to get an e to the t of L minus d minus L, and then times what we had before. So this is supposed to be the derivative at t equals 0. And if you take that derivative, you just pull down this exponent. So you get 2L minus d times x to the L, y to the d minus L. So indeed, I've chosen a basis where H acts diagonally with the indicated eigenvalue. And we can do the same thing for x and y. Let me just do it for x. So x acting on x to the L, y to the d minus L is the derivative at t equals 0 of the group element 1, 1, t, 0, acting on x to the L, y to the d minus L. This time the action isn't diagonal. Things are going to be mixed up. So this is the derivative at t equals 0. Well, nothing happens to the x coordinate. To the y coordinate, we get tx plus y to the lth power. And so if I want to compute the derivative with respect to t at t equals 0, I just want to pick out the term that t occurs exactly once, the linear term in t in this. Okay, so the linear term in t, so sorry to belabor this. So there's a bunch of other junk, and then the linear term in t looks like t times x to the L plus 1, y to the, this should be d minus L, d minus L minus 1. And what's the coefficient? The coefficient is the d minus L choose 1 coefficient, if you wish. And there's other junk. And so what I get is I get d minus L times x to the L plus 1, y to the d minus L minus 1. And you can do the same thing in the privacy of your own home or your own dorm room to conclude that this one, I guess, is probably L times x to the L minus 1, y to the d minus L plus 1. So let's draw a picture. And so this is the picture that if you're stranded on, this is the first picture you would draw if you were stranded on a desert island and you wanted to generalize finite dimensional representations on which H acts semi-simply. Okay, so we have, well, let's see. Okay. And so H acts here by minus 2d, acts here by minus 2d plus 2, minus 2d plus 4. It acts by 2d. I'm just writing down the formulas that 2d minus 4. X is going to move me. What a crappy picture already. So x goes up. Here it goes up by d. Goes up by d minus 1, d minus 2, dot, 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 2, 1. And of course, it kills the top guy. And other way going down, we have d minus 1, d minus 2, dot, 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 2, 1, 0. OK. Everyone understands the picture. It's a picture you 95% of you have seen before, have made for yourself before. OK, so the interesting thing is we know this comes from representation. So we don't have to check the commutation relations. We know that the formulas I wrote down automatically satisfy that pi of x comma y is pi of x, pi of y, minus pi of, well, why don't I do this one first, the h and the x one first. What am I doing here? Pi of h. So, and this is, after all, 2x. So we know that when we act by 2x on the left-hand side and we compute this difference, we get the same answer. That's not so interesting. If you chase that down, that just means that x has to map this eigenspace to this eigenspace. This is a familiar computation. If h acts by k on a vector v, then xh, if you just write this down, has to act by k plus 2. It just moves the eigenspaces up by 2. Same thing if I wrote down the commutation relation that y had to move these things the other way. Okay, so this means v, if h v equals kv, that implies that h of xv is k plus 2 of k plus 2 of v. So x really is a raising operator in this sort of picture. Y is a lowering operator. You have to check that. Could have this way. But the more subtle relation is the one. The more subtle is that pi of h is pi of x, pi of y, minus pi of y, pi of x. Now I encourage you to just, if you haven't checked this before, just check that if I go by y, then x, and I subtract off xy, I get what I got. What if I do by h? Okay. So when you write that down, you see what's making that commutation relation work. Okay. So so let me tell you what I mean by that. If we were to try to generalize these pictures, we might try as follows. Okay, so we know that h has to act semi-simply, so we have an n weight space, and we know that x has to take this up to the n plus 2 weight space, has to take it to the n plus 4 weight space, the n minus 2 weight space. We know that x has to go this way, y has to go this way. And if we're trying to generalize things, what we have to put in here, well, we know that h acts by n minus 2 in this weights in this space, x by n in this space, n plus 2, and so on forth. But we have to put in the numbers an, I'll label them this way, en plus 2, a n minus 2, and so on and so forth. So we want to find a basis of these one-dimensional spaces. And in that basis, we want to compute the action of x as multiplication by an minus 2, an. And we want to choose these a's and b's for the action of x and y in such a way that these relations work. So we've already built this relation into our picture, that x goes up and y goes, and the corresponding ones y goes down. The subtle relation we have to check somehow, or we have to, that imposes conditions on the coefficients a's and b, little a's and little b's that we're putting there. Okay, is that clear? Okay.
When did we confirm they were one-dimensional?
Well, we didn't quite confirm. We didn't. I said I'm just trying to generalize this picture.
At this rate,
So,
there's no justification for it
there's-
whatsoever. It just works well.
no, it just works well, exactly. So there's no justification, exactly. So I'm just trying to generalize that picture. I'm not proving it has to be that way. I'm just trying to come up with a generalization of that picture. So the simplest generalization. This is physics. This is physics, yeah. So this is supposed to be the physicist's classification. So.
It was done by a physicist.
Huh? It was done by a physicist. By Bergman in the 50s. It was done by physicists. Or 40s? I don't know. 42?
He says he wrote it in 42 and published it in 49.
Oh, I see. I don't think there was much math going on in 42. I think, but I guess Bergman was diligent. Okay, so what are the conditions that are imposed here? So, well, what are the features of these coefficients that make things that are nice? Well, let's see. If I add these numbers, notice I always get d. So if I take the diagonal sums, I always get d. And if I take the differences, I take this one minus this one, I always get the weight. So if I take, this is 0 minus, oops, it should be, or if I take this minus this, huh?
The highest weight is D and not 2D.
Oh, it's not d. You're telling me this? Yeah. Why did I get 2's all everywhere? Sorry. Okay. Yeah, so if I take this minus this, I get the weight. If I take this plus this, I always get d. Okay, so let me write this down. So the conditions on the coefficients are that an plus bn, well, let's take the difference first. So bn minus an is always equal to n. Okay, if I take this minus this, I always get that number. And so that's a condition that's in that picture, and if I'm trying to generalize, maybe I want to keep that. And the other thing, if I add them up, I always get d. Okay? And you can check that this last condition you can relax and still satisfy this commutation relation. Okay? So this one you can relax. If I add these two, don't I always get d? 0 plus d is d. 1 plus d minus 1 is d. So if I add them, I get a constant. If I take the difference, the difference is the thing that changes. That's what I add. Okay, so I'm going to relax this condition and just say that bn, that the sum of these is just some complex number. It's just some complex number. So that's.
Just write down necessary or sufficient conditions.
Huh?
Can't you just write down necessary
Yeah.
or sufficient conditions?
Yeah, I mean, these are necessary and sufficient for this to be a G module.
Okay.
These two conditions.
You haven't stated that.
No, I haven't stated that, but I don't need to. So, huh? Okay. It's only physics. Maybe I should. Yeah. Maybe actually I should state that. So I'll sketch later. I'll sketch that actually. No, actually it's a little bit non-trivial, I think. So So we'll come back to that. So all we know is that these are sufficient. At this point, let's just say you could quickly check that if you had these two conditions, you get a G module that satisfies these things. Okay. Okay. So let's draw the picture. Okay. So anyway, this is our picture. Well, we have the picture. So this is our module. If we fix a complex number, we get this. And so let's take a look at. Let's label these things. So we get for each lambda, we actually get two SL2C modules. Okay. Well, there's the one I wrote. Why do we get two? I'll call a piece of lambda. Why could they be? Oh, no. So wait, there's other conditions I want to impose. No, these aren't necessary and sufficient. No, there are other conditions I want to impose. Sorry. So, shoot, now I'm getting all tangled up. Yeah, the other conditions I want to impose is that these numbers an plus an minus 2 minus an equals 1. These numbers I want to decrease always, and these numbers I want to increase always. Okay, so shoot, I want to impose those.
This allows for creative note-taking.
Well, that's why I said not to take notes. So, for exactly this reason. Bn minus 2 minus Bn is minus 1. So I want these numbers to decrease by 1 always, and these numbers to increase by 1, just as I had in this picture. Okay. So if I have these, I get a G module. Then the A's and B's are determined by this condition lambda. Bn plus An is lambda. These conditions then specify, I know their sum, I know their difference, I know how they march up and down. I'm done, I guess. Okay, so I claim we get two families. So there's P plus, this is if n is even. So that's when the weights will just be even. And then there's P minus of lambda if n is odd. Okay. Okay, so we've, just by looking at finite dimensional representations, generalizing, well, or at least keeping track of some of what finite dimensional representations look like, relaxing one of the conditions, we get this family, or actually two families, whether or not we hit the even eigenvalues of H or the odd ones.
If lambda is an integer, wouldn't you get many more, some highest weight, some lowest weight, some...
Yeah, no, I'm not saying these are irreducible or anything. So, these are not irreducible. Huh? Necessarily. So let's take a look. Let's take a look. Let's take a look. Let's take a look. So we'll draw Bill's pictures now. So qualitatively, what happened? Okay. Let's see. So if lambda is a positive integer, well, then we're in a situation where we've got this string. It just looks like the finite dimensional case. But somewhere we hit 0, just like the finite dimensional case, but we just keep going. All these other arrows, if they're not a squiggly arrow, they're non-zero. And so maybe I should put 0 is the center of this diagram. So this is just the picture that we had for the finite dimensional case. But we've just extended it to all weights. Is that clear? Okay. So if lambda is less than 0, yeah, in this case, yeah, sorry. If lambda is a negative integer, then what is the picture that we get? Well, again, we have the raising and lowering operators. If you think about what those conditions impose, lambda being less than 0 means that these raising operators will all be negative, negative, negative. Where I get a 0 is back here. Okay. And where I get the 0 this time with the lowering operators is somewhere over here. Okay. If lambda is not an integer, I'm never going to get 0. I'm going to these numbers are going to be non-integral. I'm going to be subtracting off 1 or adding 1. I'm never going to get 0 anywhere down the line. Like this. And if lambda equals 0, there's sort of a degenerate case where these kind of overlap and sort of shrink to nothing in here. So maybe that's a good thing to do at lunch. So draw the picture for lambda equals 0. OK, so what we see here then is, OK, so now it's audience participation time. So which of these are irreducible, or what do these look like? Is this one irreducible? We'll start with the easiest. Does this have any invariant subspaces? No, because if I start here, I can get to any other place by either going up or going down. I'm never going to. None of these arrows are 0. None of the raising or lowering are 0. So p plus or minus lambda, which is not an integer, is irreducible. OK, so we've succeeded in constructing a bunch of irreducible so-called Harishchandra modules in this way. What about these guys? Does this, let's see which one. Does this have a submodule? Can you see any nice submodule here? What is an invariant subspace? Are there any invariant subspaces in any of these things? Huh? Yeah, the finite dimensional guy right here, right? If I take a look at the span here, then I move around. I don't get out that way. I move around. I don't get out that way. This stuff feeds into it, but we don't care. This is a subspace. Okay, so let's call that f of d. We can call this d plus of lambda. Well, maybe I should call it f of lambda. And this is d minus of lambda. So the composition series for this guy as a representation of SL2 is, well, f of lambda is a submodule of p of whatever this guy is. And actually, this is actually specified. Lambda determines, I mean, where this arrow ends, whether this is even or odd. I mean, lambda tells, where the 0 is tells you whether these points are even or odd. So I think this is supposed to be minus the parity of lambda, maybe, or plus or minus the parity. And then after I quotient out by that, if I erase this guy, then these guys are each representations on their own, which form direct sum. So. Yeah. The parity, so epsilon is determined by the parity of lambda. So actually, I realized I skipped a page in my notes where I actually wrote a few more explicit things down. Maybe that would have made things more comprehensible, but oh well, it's too late now. So this one, what happens? What are the submodules on this one? The finite dimensional guy, if I stay in here, if I try to see if this is a submodule, the span of these weight spaces, but I move out of that one, and I move out of that one. So that doesn't work. What about this guy? If I'm here, I'm raising, I don't move out of it, and I don't move out by going down. So in this case, I have d minus lambda, which is a sub, d plus lambda, which is a sub, and again, this parity, there's the same pop-up window about this parity here. And then once I quotient out by those, if I mod out by those two, what I have left is a finite dimensional. Okay, so, and then this one is irreducible. And everything that I've written down is then irreducible. There are no invariant subspaces of any of those things. Yeah.
Epsilon is determined by lambda.
Epsilon is determined by lambda. Huh?
It only depends on lambda.
Well, but there's another one. So epsilon is determined by lambda, and I get this reducibility. But if I had the other one, then it would be irreducible, because it would never encounter 0.
No,
Yeah.
Does it depend only on lambda, or is it?
Okay, so I think I've made it. Well, I've probably made it. Okay, so let me write. Let me write some. Let me write these formulas, which I said I omitted, and then it will become clear. Well, probably not. Okay. So these are the formulas for these modules: p epsilon plus and p epsilon minus. And we're going to take 1/2 lambda minus. You wouldn't believe how much I agonized over these stupid formulas last night, and then I forgot to write them down. It's very disappointing. These describe some transition coefficients for raising and lowering. If epsilon is plus, I take my ends to be even. If epsilon is minus, I take them to be odd. Okay? So if I encounter a 0, so now think of lambda as being a fixed positive integer. If I encounter a 0, I'll only get a 0 when either the weights are determined. I think it's the opposite parity of lambda. The other one, I won't get 0. I'll be off by 1. Okay, so maybe I should say this. So p of minus the parity of lambda, and I just checked in my notes. That's correct with those formulas. Okay, this one reduces, but then p plus the parity. I mean the parity of lambda is irreducible for this lambda a positive integer. Do you understand what I'm saying? So they come in two flavors. Even for the positive integer, only one of them is reducible. The other one is irreducible. Okay. The same remark applies down here. So epsilon is minus the parity of lambda. Okay. If I took the other parity, the other weights, use those formulas, I get something irreducible. Okay, so the point is that so what are you supposed to take away from this? What you're supposed to take away from this is that you wrote down the finite dimensional representations. They had some structure. You wrote them down in a nice way. You relaxed the condition on the raising and lowering to not be integral, but to have this complex number lambda. Okay? You wrote them all down. You analyzed the structure. Sometimes they're reduced. You understood the reducibility exactly in terms of these exact sequences. And in this way, you built a long list of irreducible so-called Harish-Chandra modules. The irreducible representations of SL2C were HX semi-simply with integer eigenvalues. Okay? So now we have a big catalog. We've got the finite dimensional guys. We've got these ones that go off positively. We've got the ones that go off negatively. And we've got the ones that are a whole line worth of stuff. Okay? And the classification is that this is a complete list of irreducible. So now I'll start calling them GK modules. So that, again, that's representations of SL2C where H acts semi-simply with positive integer eigenvalues. And so this is a complete list. We've got these P, the irreducible P's. So this is P plus or minus lambda, where lambda is not an integer. And we've got P, if I take the opposite parity, lambda is, I think even 0 works there. And then we've got D plus and D minus lambda, these ones that go off. And we have f of lambda. And so for these, so lambda I can just take to be a positive integer here because I'm getting some duplication. That's another thing I haven't said. So this is the same finite dimensional representation that's showing up here and there. I should have remarked when I wrote down the formulas for finite dimensional representations that the formulas I wrote down exhaust all finite dimensional representations. So we're not getting new finite dimensional representations in this place and in this place. They have to be the same one. What's a little less obvious is that these D's are the same. Here I've got a positive lambda and a negative lambda, but nonetheless, these things that go off to the negative side are both equivalent. Okay, so that wasn't obvious from what I had said, and it still isn't obvious from what I've said. But nonetheless, this is the list. Okay. So the question is how you prove this list is complete. Okay, so we know already one of the things what I should have remarked on is that those formulas I wrote down classify all finite dimensional representations. So we understand that these are all the finite ones on the list. Okay. Let's understand why these formulas determine, say, these guys completely, the ones that go off in one direction and not the other. Okay? So this is pretty simple, and then that'll be a good place to stop. Okay. And in fact, I'm hiding the most serious calculation, which is the ones where they don't go off one direction or the other. Okay, so here's a piece of the proof. Okay, suppose we have V, which is an irreducible GK module for SL2R. Those are the objects. I haven't used that language except on the previous board, but those are the objects we've been studying. That's the name for them. And right, the decomposition according to the action of H. Okay. And suppose there exists V, a non-zero V, in V sub k, say, such that xv sub k equals 0. Now I'll call this little v sub k. So I march along somewhere in my strand. I've got this strand of stuff. These don't have to be one-dimensional. We've never said that. As Abba pointed out, there's no reason to assume that, but I can still look at these possibly larger dimensional spaces. In the kth space, I find some vector which when I apply x, and I know x has to go up from the basic commutation relations, I get 0. Okay? So then let's let v prime, that's maybe w, be the span of what I get by applying y to this special vector that's killed by x. Y vk, so vk, y vk, y squared vk, and so on and so forth. Okay, so in your head, you're just picturing a strand marching off to the left. Okay. So I've got this CVK. Well, okay, so now pick VK minus 2J in, pick a basis of this W. Say, well, start with my given basis vector, the one that's 2 below it. Did I mess something up?
I'm just wondering, why is there a vector that's killed by x?
That's what I'm supposing. So this is just a piece of the proof. So that's good. So what I'm doing is I'm given one, and I'm supposing it has this form. I want to see, so this is a special case of the proof. I want to see that that's on my list somewhere. Okay? Okay, so I take this strand off. I pick a basis where vk minus 2j actually lives in this eigenspace of H. Okay. And I scale the basis. So the x action is as follows. So I've got this one-dimensional space spanned by CVK, CVK minus 2, CVK minus 4, and so on and so forth. We know that x acts by 0 here. Now, if x doesn't act by 0, I can scale the basis so it acts by 1. I can pick the basis so it acts by 1. If it doesn't act by 0 here, I can scale it x by 2, 2, 3, and so on and so forth. What if at some point I encountered a place where it did act by 0? Well, then I would have an irreducible subspace, right? Because these guys would be trapped by x and oh no, that's not right, is it? Yeah, I know, I know. Let's see. Huh? What's that? But why does x never have to act as 0? Huh? Yeah, that's the point. Yeah, if I had a 0 here, if x acted by 0, now this wouldn't be a subspace that was irreducible, but invariant subspace. But this would be exactly. So there can never be a 0. So I can always scale these numbers like this. Okay. And then I simply use my commutation relation to figure out what these numbers have to be. So xy minus yx is equal to h. If I apply that to vk, I figure out what this has to be. And I think this has to be, this tells me, so apply this. So applied to vk implies, you just do a short calculation, that y applied to vk is this basis vector, this rescale basis vector is k times vk minus 2. So it looks like this. And then once I know what this guy is, then I know the next one, which actually has to let's see, if these numbers decrease, these numbers do increase. So this is k minus 2, k minus 4, and so on. And that's on my list. Minus 1, I guess, yeah. Maybe we should do it. So, well, maybe I won't do it. So, but you see the procedure. Once you have this highest weight vector that's killed, then you scale the basis. You can't have a 0 anywhere. Otherwise, as Lee points out, you would have 0, an invariant subspace over here. So you apply your commutation relation to figure out what y has to do in this basis, and that's something that's on your list already. So this is d minus of k, perhaps. This is on the list. So as I said, this was just a piece of the proof. If I took an irreducible guy that had a highest weight vector, it was very simple to see what the structure of it had to be, and that was something that already appeared on my list. So I would have to just do this. I mean, the argument is the same. If there's a vector that's killed by y, that's identical. Slightly more complicated is if I have a situation where there's an entire string, there's nothing killed by y, there's nothing killed by x, and I have to identify it as one of these things on the list. Okay? There are various clever ways to do that, but they all amount to just playing with the commutation relations in some clever way. So it doesn't seem too worthwhile to do that now. But here's the scheme. So you take a look at finite dimensional representations, relax them in some natural way. You get this larger class of p's that are generally reducible. Some of them are irreducible. Otherwise, you identify sort of these highest weight strings, these lowest weight strings, the finite dimensional representations you already know about, and then that list is complete. The point is, if you go back to the beginning, why is this a useful classification? Well, on this list, you get every GK module gotten by differentiation restricting to these so-called K-finite vectors arising from an irreducible unitary representation of SL2R. So this is an appropriate, so this is an interesting list because it contains the parameters of unitary representations for SL2R. It contains more. We'll have to see that later in the week. But that's the place to stop for now. So have a good lunch and see you back.